My name is Jian Ding. And I will present you our paper on decoupling zero-shot semantic segmentation. Although remarkable progress has been made, the current segmentation models have two limitations. First, they often require hundreds of samples for each class. Secondly, they are often trained with a fixed set of predetermined categories, assuming we have the same classes for training and testing. But in the real world, the testing data may contain the classes which we have not seen during training. Humans can distinguish at least 30,000 basic classes, and recognize novel categories merely from free-form text descriptions and their relations with basic classes. How to build segmentation models that reaching human recognition ability. Transfer the knowledge from seen classes to unseen classes is usually studied in zero-shot learning. SPNet is a representative work for zero-shot semantic segmentation, which follows the pixel-level classification formulation for semantic segmentation. Then it projects pixel-level visual features to semantic space, and compute the similarities to word embeddings. The final classification is made according to the word embedding with the maximum similarity. The drawback is that the pixels do not have rich semantic information for zero-shot classification. Our method is based on the observation that we can easily get the boundaries of objects, even though we don't know their names. Therefore, we decouple the zero-shot semantic segmentation into two subtasks. The first is a class-agnostic grouping to group pixels into segments, which can be easily transferred to unseen classes. The second is a region-level zero-shot classification to assign semantic labels to either seen or unseen segments. The region-level features contain richer semantic information than pixel-level features, which can benefit the knowledge transfer from seen to unseen classes. Formally, an image is defined on the domain omega, which includes h times w elements. Semantic segmentation can be defined by a pair of mappings. The first one maps the image domain into n disjoint sets, such that the union of them equals omega. The second one maps segments to a semantic label to seen classes during training, while both seen and unseen classes during testing. In practice, we use probability mask to represent segments. Now, I will introduce the detailed pipeline of our method. In our model, n queries are sent to the transformer decoder. Then there are two projection branches to generate n-mask features and masks, respectively. Then we generate the text features for k classes from a pre-trained text encoder, for example, clip. Then, we compute the similarities between segment visual features and text features. The classification for segments are made according to the text features. This model is called zeg-former-seg. While the steps mentioned above can form a standalone approach for zero-shot semantic segmentation, the model trained on a small dataset is struggling to have strong generalization. Thanks to the decoupling formulation, it is also flexible to use a pre-trained image encoder on a large dataset to generate image embeddings for zero-shot segment classification. This model is called zeg-former-image. The performance of zeg-former-seg and zeg-former-image on different classes are shown in the right picture. We can see they are complementary. So we fuse the two kinds of classification scores, and obtain the final zeg-former model. We evaluate models in both class-aware and class-agnostic metrics. We also compare clip with traditional word embeddings. We can see that clip is better than traditional word embeddings. Zeg-former is better than the baseline in all cases. Zeg-former has larger gain when embedding method is changed to clip. In the very challenging ADE20K full, zeg-former is very close to a fully supervised mask former. Zeg-former outperforms the previous methods by large margin, without the need of self-training. It also does not need to be retrained for new classes. Here are some visualization results. The models are trained on 156 classes of Cocoa Stuff. During testing, we generate 171 classifiers according to the classes on CooStuff. In this visualization, the models are also trained on 156 classes of Cocoa Stuff. During testing, we generate 847 classifiers according to the classes on ADE20K full. We can see some interesting results. Our predictions provide even more fine-grained class information than Cocoa Stuff annotation. For example, the annotation in the yellow bounding box is just a house, while our prediction is garage, which is more precise. Thank you for listening.